So as we're continuing in the meteorology unit, now we are getting ourselves into the next section as we talk about the atmosphere. We just finished talking about the layers of the atmosphere. Now we're getting the idea of how air moves within our atmosphere. Because you could probably agree or attest to the fact that air movement is actually what causes weather to move from one area to the other. Now, as we're going to learn later on, water is what makes up weather. Obviously, condensation and clouds and precipitation being rain and storms, and you got hurricanes and tornadoes. But something moves all of that water in the air, and that's going to be the air itself. The air is going to move those pockets of weather from one place to another. So there are different types of winds, which is just air movement, to actually cause weather to travel from one place to the other. So it's not just localized in one area, it continues to move on a global level. And then we'll talk about how winds can be centralized to a very local level depending on what area we're talking about. So in order to understand that, we got to understand what wind is. And wind is a very simple definition of what wind is. Wind is just moving air, air that moves from one place to the other. Now, what causes wind or air to move from one place to another? Well, we have differences in air pressure, from areas that are high pressure to areas that are low pressure. And usually air tends to move from areas of high pressure to areas of low pressure. Think of it this way. Have you ever noticed that one day of the week, let's say today, it's 60 degrees outside, and then you go outside the next day and it's 30 degrees outside, or maybe 20 degrees outside. This cold snap has come through, or a cold front has moved through, as you're learning this unit. Well, did you also notice that with the extreme temperature drop that the air is moving a lot more, you're experiencing a lot more wind? That's because one day your day was 60 degrees, the other day your day was 30 degrees or 20 degrees, whatever you decide to be, and air is tending to move from times that the air is warmer to air that's colder and vice versa. So a lot of times when we have dramatic shifts like that in temperature, it's usually characterized by very windy days. So you see that in the trees as the trees are blowing around in the wind. As we talk about air movement, though, we're going to kind of focus on the idea that air will tend to move from areas of high pressure to areas of low pressure. So what we get into next is, what does that mean to be high pressure and low pressure, based on what we've talked about with air pressure already. For this slide, I'm going to bring myself into the demonstration so I can kind of talk about the difference between high pressure and low pressure. So as we talk about high pressure and low pressure, you have to think back to when you studied in chemistry the idea of solid versus liquid versus gas. Okay, gas molecules, you remember, were moving so much faster. So if I put my two fists together, I can simplify here. Solid, look, they're not moving. Those particles, those molecules that make up that solid are not moving, or they're vibrating in place. They're really not moving a whole lot. But as you add heat, the solid is turning itself to a liquid, so those particles start to move even more, okay, from that vibration, and they start to kind of separate from each other. And then as a gas, they really start moving away from each other, and they start even allowing more and more space to kind of take place. Well, now let's centralize this to a gas idea. With gas particles, when gas is cooler, if it's cooler air, you've got more and more molecules that are starting to do this. They're starting to come together. There's so much more in that area that the amount of air molecules basically indicates you have what's called high pressure, because high is in this case indicating a lot of different air molecules in a space. And since they're cooler, they start to pack into each other. That's where it's just before these gases are going to start turning to liquid that they start to kind of bond together and come together. So when something we say is high pressure, it usually looks like this. It usually looks like molecules that are higher number gathered in a localized area, a small area, and that high pressure just means more in this case, so high equals more. So cold air is usually an indication of high pressure. Low pressure means you've got warmer air. So those molecules that are warmer, if you're heating them up, they're going to start moving even farther and farther apart from each other. So there's not going to be as many in that area that you had before. And what happens then, that leaves room for other molecules to fill that space, specifically water. So when you have low pressure systems, a lot of times you've got really warm or hot air because those particles are moving so far apart from each other, and it allows water vapor to kind of sneak in and be part of that equation too. So sometimes you're going to have climates in these lower pressure areas that are warmer and wet. So you get the rainforest, you get the areas of rain, pockets of rain. When you look at a barometer, as we talked about air pressure in the last unit, we've talked about a barometer. The lower pressure means lower air molecules, which gives way to the water vapor molecules to kind of fill that space. So low pressure usually is an indication of wetter weather because there's a lot of opportunity for water vapor to condense and then precipitate and fall to the earth. So higher pressure usually indicates colder areas, and we'll talk about this on a global level next. But then also low pressure areas kind of indicate warmer areas. So now we're going to start making the connection between what you've learned in seasons in astronomy to how the Earth is heated to why is there different areas of pressure on the Earth. So to take the connection back to what we learned in seasons back in the astronomy unit, at the end of the astronomy unit, to give you the idea that the Earth is not evenly heated because the Earth doesn't sit in like this picture. It doesn't sit nice up and down, straight up and down. It's actually tilted. So certain areas of the Earth get different amounts of sunlight. Some parts of the Earth get no sunlight at all through 6 months of the year, and some others get constant direct sunlight all the time. So the question I asked you is, okay, where on the Earth is it hot and cold? Now, connect that to what we just talked about with high pressure and low pressure. Low pressure areas are those areas that are going to be a lot warmer or hotter and sometimes more wet, but sometimes they're desert areas too. So therefore, your low pressure system that's getting the most direct sunlight all year round, that's the equator. So the equator is an area on the Earth that's considered a low pressure area because it's hot. It's hot all the time. The sun's direct light is converting to thermal energy in that location all year long. That's where you're finding the locations of tropical rainforests. When people like to vacation in the Caribbean, they go to an area that's much warmer. This is a great area for that. So these are areas of low pressure. And then where else on the Earth that it's, so if we're talking about the cold air, now we get into areas of high pressure, because high is usually colder air. There's more molecules in that location. And there's two areas on the Earth that are generally cold, and that would be the poles. So the North and South Pole are generally areas throughout the year that are much colder. So you've got different pressures all over the Earth because of the uneven heating of the Earth. You've got areas of high pressure at the poles, you've got area of low pressure at the equator, and since air tends to move and travel from areas of high pressure to low pressure, you're going to get a lot of air trying to make its way from the North Pole and the South Pole to the equator. So that's what's leading us into the fact that on a global level, we have air moving all the time. Now, you might be sitting there and asking yourself, well, then why isn't the equator moderate or cool? Why is the extreme hot? Why are the poles, not warmer than what they are? Problem is the air is going to start moving, and you're going to see on the next slide, the air is going to start moving from the high pressure areas to the low pressure areas, but then eventually in the convection current style, eventually it's going to warm up enough that it's going to return itself back towards the pole. So I'm going to show that to you on the next slide. So on a global level, we said that air can move from areas of high pressure to areas of low pressure. So from here down to here. Okay, areas of high pressure and areas of low pressure. Same with the South Pole up to the North Pole. However, the second these molecules of cold air start leaving the North Pole, where it is the coldest, or the South Pole, where it's the coldest on Earth, they do begin to warm up. Now, if you can remember, we talked about convection currents. Convection currents is a movement of air where warm matter, air, water, whatever, in this case we're going to talk about air, warm air will always rise and cold air will always fall. So in this case, globally, north to south, okay, the cold air is falling and the warm air is rising. So technically, let me erase this. If I'm bringing cold air down from the poles, okay, down here, just want to make sure you can see that, and warm air is going to move up from from the equator, technically what you have on a hemisphere level is a huge convection current. Okay, actually, and this is true when it comes to ocean currents. Ocean currents will move this way, well, the deep ocean currents do, not necessarily the surface ones. However, again, like I said, it's a long distance from the North Pole to the equator. So what happens is, if I go back to my cold air model, what happens is the cold air will begin to fall from the North Pole, but then it's going to stop about here, about 60 degrees latitude. Because at that point, it's going to start warming up, because it's warmer than what it was at the pole, and that air will make its way back to the North Pole. That same phenomena is similar here too. You got colder air falling to a warmer location to about 30 degrees latitude, and then you've got some of the warmer air moving its way back up. So these pressure belts are really big convection currents, and on a smaller level than just the hemisphere is kind of broken up into 3 sections of pressure belts. Same idea here. It's cooler at 30 degrees north latitude than it is at the equator, but at the equator you've got warm air that's making its way more north because warm air rises and the cold air falls. Okay, southern hemisphere, because it's upside down, if I flip the Earth upside down, it shows the same model and method. So I'm going to focus just on the northern hemisphere. I'm not going to draw these pressure belts throughout, but the same types of pressure belts happen in the north and in the south. Perspective is going to be changed because technically on the southern hemisphere you're kind of upside down. Okay, so that's what pressure belts are. It's pretty much convection currents that occur from between 30 degrees of latitude, North Pole to the 60, 30 to 60, and then the equator to 30. So what this is going to do is it's going to create global winds and global air movement, but it's going to happen in certain directions, and that's what you're going to see on the next couple of slides. But before we talk about that, I keep drawing these arrows as if they're straight up and down, when in actuality, because the Earth rotates, these lines are actually curved. So we're going to talk about that next. So this is one of your definitions for your glossary, so it's up on the screen for you. But it's actually a pretty simple ideal. The Earth rotates. We learned that in astronomy. The Earth rotates at a certain speed, and it takes 24 hours to make one complete rotation. We talked about that as well. But that has an effect on the way air and water travel across the Earth's surface. What happens is with the Coriolis effect, and if I had a spinning object, if you spun an object and you took a marker as the object is spinning and tried to draw a straight line, the object would actually curve, or the line you drew would actually curve. Well, that's true with the Earth. As these pockets of air are trying to travel from either the North Pole towards the equator or vice versa, what's actually happening to them is they're curving along the way. That curving effect is what's called the Coriolis effect. So, which means that air could move from north to south, but when it's done moving, it's not traveling north to south or south to north. It's traveling east or west, depending on what part of the Earth we're talking about. So when you see me draw the next arrows on the next pages, what you're going to see is a curving of the air, the global air, as it moves from one area to the other. And that curve is due to the Coriolis effect. So air and water will have the reaction of curving as it's moving across the Earth. That's what the Coriolis effect is. So now we can kind of name these sections of the Earth. So the pressure belts in each of these 3 sections of the Northern Hemisphere, there's actually names that go along with each of these types of wind belts. And we're going to focus the direction of the wind. We're going to focus from areas of high pressure to low pressure, because that's what I said, air tends to move from areas of high pressure to low pressure. And the way they curve actually indicates which way the winds on a global level tend to move. Some directions will be east to west, some will be west to east, so it depends on where the air is starting from. If it's the cooler, high pressure air, air will tend to move from areas of high pressure and low pressure. So in the first wind belt, which is going to be the North Pole down to 60 degrees north latitude, what you're going to see is a movement of air like this. Okay, air is going to tend to move from the northern hemisphere down, or from the North Pole, excuse me, down towards the equator, but at 60 degrees is going to turn around and go back towards the North Pole. Well, air will tend to move. It'll start from the north, but it'll tend to move towards the west. So this type of wind belt, and it happens on a global level, it's not just one line of wind, it's the whole section of between 90 and 60, is called the polar easterlies. Now the name is coming from, obviously, the pole, North Pole, South Pole, whichever pole it's starting from, but the fact it's coming from the east and heading towards the west. So where it's coming from is where it's part of its name, not where it's going, where it's coming from. So the polar easterlies are the wind belt that sits between the North Pole and 60 degrees north latitude. Now, the wind belt that you are most accustomed to, because you live here in Boyertown, okay, somewhere in that red dot there, since you live this part of North America in the United States, in Boyertown and Gilbertsville, wherever you are, what you experience is a different direction of wind, to the point where it seems like weather always starts, let's say I put a star over here, and a couple days later it's moved like this, and a couple days later from that maybe it's moved this far, depending. Okay, that is considered a west to east movement, and that's because we are in the wind belt that's typically called the westerlies. The 30-degree north line is the line of high pressure, and the air moves from west to east, so we call it the westerlies. So think of this on a global level. If you are a sailor in this part of the world, especially back in the 1500s when there was no such thing as a boat engine, you basically sailed because of where the wind took you. If you had to get yourself from America, the New World, back towards the Old World that you came from, you'd basically let the wind carry you all the way across the sea, in this case. Now, think about that for exploration coming this way, though. They couldn't get over this way without going farther south first and then working their way up. So the Jamestown, Roanoke settlements, even Plymouth Rock settlement, for the Puritans, the Pilgrims that came in there, they had to sail quite a ways south before they actually worked their way north towards where Massachusetts was. Anyway, back to science, and not so much a social studies lesson. Same idea. So 30 degrees is our high pressure system, and winds tend to move from north to south. 30-degree line will also create what's called the trade winds. So from 30 degrees north down towards the equator, remember 30 degrees is cooler than the equator itself, the winds will tend to move again from the east to west. But that section of the northern hemisphere is called the trade winds wind belt. So you've got three main wind belts: polar easterlies, westerlies, and the trade winds. And what I'll do on a separate worksheet and a separate demo is kind of map that out for you so that you can see it on a larger scale. This is kind of a smaller introduction scale. Another example of a global wind, you might hear on the news when they do the meteorology reports, they do the weather reports, and they talk about the jet stream. Okay? The jet stream is pretty much a high-level wind. It sits up in the upper troposphere, and it travels a good distance. It stretches quite a long way. It's a narrow band of high-speed wind. Now, this is not one of your key terms, so you don't have to define this, but I just want to introduce it to you. A narrow band of high-speed winds that can influence and drive weather. And for us in the westerlies, the jet stream tends to move, in North America, tends to move from west to east. And in the picture is an example of the way the jet stream can look. That jet stream that you're seeing, that band of wind, sometimes drops lower, sometimes moves higher, and a lot of times it is a good separation between the areas that are warmer, which would be the south, and the areas that are cooler, which would be the north. So when you get a jet stream like the picture here, a lot of colder air is hitting the Midwest, as you see in the picture, and almost to our area. But if the jet stream stretched up into Canada, then we'd experience more of the warmer weather. So the past couple weeks here in Gilbertsville and Boyertown, it's been warmer. It's because the jet stream's been a little bit more north. So we've been getting a lot of the warmer air from the south moved up into our area. The week or two before that, when we had the polar vortex, that jet stream had dropped so low into the United States that a lot of the colder air from Canada came down into the United States and gave us some record low temperatures, and especially in the areas like Chicago and states like Minnesota experienced some of the coldest winters they've ever had. And it's because of that jet stream. The jet stream is going to move weather, and it doesn't really have a rhyme or reason to when it's going to blow in a certain direction, when it's not. So when it does, though, meteorologists are going to keep track of it because it's going to give them a good indication, especially when it comes to prediction, of which way the air is traveling. So that's all the winds on a global level as the whole Earth is concerned. But there's actually other types of air movement that occur on a more localized level. So think of it this way. When's the last time you were at the beach? During the day and during the night, did you notice that while you're at the beach, if you've ever been to the beach, do you ever notice that the air tends to move a lot at the beach? It's a good place to fly a kite because the wind seems like it's constantly moving. Well, those types of breezes, whether it be day or night, those types of breezes are considered local winds because they're localized to a certain location, a certain area. So, with that being said, let me flip the slide here. It's still because of uneven heating, but it's just not happening on a large scale. In this case, it's happening on a localized level. So the question becomes, well, what is being unevenly heated? If you're at the beach, you've got two substances there, a solid and a liquid. You've got land and you've got water. They absorb and release the sun's energy at different rates, which means that they do not absorb it the same and they do not release it the same. One of the two releases it more quickly, one of the two absorbs it more quickly, and then vice versa, one of the two absorbs it slowly and releases it slowly. All right? Because the fact that the land and the water heat unevenly gives local areas like this wind, air movement. So this is what's a good example of a local wind, the sea breeze versus the land breeze. So we'll talk about that on the next slide. All right. So for example, water slowly absorbs solar energy. So when the sun rises in the morning, the water is very slow to absorb that solar energy. It takes a while for the water to warm up. And then later on, it does. And when the sun goes down, the water takes its time to release that solar energy back into space or back into the sky. It's because, well, I don't know why. It's because it's just the water just absorbs and releases that water slowly. So if you think of it in a high and low pressure system, remember high being cool and low being warm, during the morning hours, the water is considered high pressure because it's cooler. At night, even though the sun has gone down, the water is still warm, so therefore it's considered a low pressure system. Air is going to tend to move from areas of high pressure to low pressure. Okay, keep that in mind. Because the opposite effect is going to happen to the land. Land, on the other hand, has the opposite effect. During the daytime, the land will absorb the heat very, very, very quickly. And then at nighttime, when the sun goes down, the land loses all that heat very, very, very quickly. Okay, so during the day, since it's absorbing the solar energy just as soon as the sun rises and hits the radiation hits the surface and converts to thermal energy, as soon as that takes place, the solar energy that's being absorbed heats that ground. Now you've got warmer land, so therefore you got a low pressure system. And at night, it releases all that heat energy so quickly, so it's a lot cooler, so you got that high pressure system. The example I can give you with land is a desert. Deserts are hot in the daytime and they're cold at night. Why? Because there's nothing to keep that heat. It absorbs that heat quickly in the day and loses it overnight when the sun goes down. So you've got deserts are usually hot in the day, cold at night, because it loses and gains gains that heat so quickly that it creates that opposite effect that what water does. A good example of water too is the ocean. The ocean will heat up over the summer, but usually it's not until June or July that it gets really warm enough that especially if it's a hotter summer, that people could actually like to go swimming in it. But as the temperatures drop in September and October, the ocean water takes a while to really cool itself down. So a lot of people like to go to the beach in September when school's back in session because the water's still warm. The air temperature is not as warm, but the water's still warm. People like to go and spend time in that. So here's what I need you to do with these two pictures. This is an example of a sea breeze and an example of a land breeze. Left is sea breeze, right is land breeze, as it's labeled there. Please draw these pictures in your science journal so you know the difference between them. This is a great example of a local wind where air is constantly moving. But depending on which area we're talking about, or if it's day or night, depends on how the air is moving. During the daytime, since the water is cooler than the land, because the land heats up quicker, it's low pressure, the water heats up slower, it's high pressure, air will tend to move from areas of high pressure to areas of low pressure, again, making that convection current. You're going to see that a lot as we talk about through this unit. Okay, so the air will seem to be coming from the sea. Like if you're standing on the beach, you're feeling a breeze coming from the water hitting the land. At nighttime, it's the opposite effect because now the land has lost all its heat. It's now cooler. The water loses its heat slowly. It's now warmer. The high pressure areas are over the land, low pressure areas over the sea, and so now the air is moving from the land towards the sea. So there's two different directions, day to night, that creates this air movement, and again, just on a localized level. If you've got areas of just land or areas of just water, you don't have uneven heating. It heats all the same. But since you've got land and water and they absorb and release heat at different rates, you've got uneven heating, and it's what causes these breezes. Finally, the other local wind we're going to be talking about is the idea between a mountain and a valley breeze. I don't know how much time you spent at a mountain or in a valley, but they actually have different heating occurrences as well. And what happens is because of elevation. Now, we've talked about air pressure. The air pressure is always greatest, the closer to the surface you are. And the higher up a mountain you go, the cooler and cooler and cooler it gets because there's less air molecules, there's less transfers of heat that are available in that case. So in higher elevation, you've got less and less air molecules. That's why people that want to climb like Kilimanjaro, K2, Mount Everest, they usually take oxygen tanks with them because the oxygen is so sparse up there because more of the oxygen molecules have been pulled by gravity to the surface. Because of these areas of elevation, different elevation, now you've got a true convection current that's going to take place in these areas. So I'm going to show you the two pictures, and again, draw these two pictures in your journal to give you an example of a mountain breeze and a valley breeze. So, and again, it has to deal with day to night. So I'll show you the day picture to start. What happens in the daytime? Now this one's not going to be so much high pressure to low pressure. This is going to be a lot about warm versus cold. Cold air falls, warm air rises. So what happens is the warm air in the valley that's being heated first will rise during the daytime as the sun is hitting the valley, will actually travel its way up the side of the mountain because warm air rises. Okay, as it gets to the top of the mountain, if it cools down, it'll come back down and make a nice convection current there from valley to mountain. So you get a nice valley breeze during the daytime because the cooler air is there, it's starting to warm up, and as it warms, warm air rises and rises its way up the mountain. At night, the opposite effect is taking place. In this case, now you've got the cooler air, which is cooler than the valley air, coming down the mountain, and a nice breeze is coming off of the mountain into the valley. So that's what we call a mountain breeze, because the cooler air is falling. It's more dense, it's falling, and if it warms up on the mountain floor, because again, higher elevation is cooler than the lower elevation, it warms up and it'll start to rise again and make that convection current again. So this type of local wind is due to the convection current idea. The warm air rises, cool air falls, and this is a really good example of both of those. It doesn't necessarily have to deal with the high and low pressure in this case, but it deals with that convection current idea. So this is an idea just to give you, as we start to learn how to predict weather, this gives you an idea of how air movement can actually cause water movement, which is what leads to weather, condensation, precipitation, whatever, and how that's going to actually affect what areas of the globe are actually going to receive different types of weather, and how it doesn't always just happen in one location. It's mobile, and can move from place to place.